And when I say major collapse, I'm not talking about a few city blocks. I'm not talking about a few townships. I'm not talking about just a few counties. I'm talking about states.
What happens when the sun, the source of all life, suddenly turns against us? Could a single storm really plunge continents into darkness, cut the internet's arteries, and silence satellites in orbit? And how close are we to finally predicting these cosmic tempests before they strike? From the Carrington event to the Inouye Solar Telescope, the race to read the sun has never been more urgent. High on the summit of Haleakala in Hawaii, the Daniel K. Inouye Solar Telescope has begun peeling back the layers of our nearest star. Its very first images showed the sun not as a smooth disk in the sky, but as a seething ocean of plasma, broken into cell-like structures the size of Texas. Each one rises, cools, and sinks in a restless cycle of convection. The view is mesmerizing, but it's more than beauty. These details are the fingerprints of the sun's magnetic fields, the same tangled forces that trigger storms capable of shutting down satellites, GPS, radio signals, and even entire power grids on Earth. For decades, predicting those storms has lagged far behind everyday weather forecasts.
Communications to GPS accuracy to currents building up on the electric power grid, which is really what our country is concerned about. So we do a lot of support to this, aviation communities, NASA and space launch, and astronaut safety.
In 2017, while Hurricane Irma battered the US, a solar storm at the same time knocked out emergency radio channels for hours. Scientists worry that the next major outburst could do far worse. The Inouye telescope changes the equation. With the sharpest solar vision ever achieved, it can follow magnetic fields from the sun's surface all the way into the corona, the million-degree atmosphere where eruptions are born. That leap could stretch our warning time for solar storms from less than an hour to nearly 2 days, turning panic into preparation. Building such a machine was no small feat. Its 4-meter mirror, the largest ever aimed at the sun, concentrates a searing 13 kilowatts of energy. Miles of pipes, liquid-cooled plates, and a special heat stop keep the system from frying itself. An off-axis design avoids glare, while adaptive optics tame the blurring effects of Earth's atmosphere. The result is astonishing clarity. Instruments like the Visible Broadband Imager can spot features only 24 kilometers wide, more than twice as fine as anything seen before. That power paid off in August 2024 when Inouye captured its first X-class flare, among the most violent explosions the sun can unleash. Within it were coronal loops thinner than anyone had ever witnessed, arching filaments of plasma only 48 kilometers across. Long imagined in theory, these delicate strands may be the building blocks of solar flares, the atoms of magnetic eruption. For researchers who had spent their careers modeling such structures without ever glimpsing them, it was a revelation. Before Inouye, we could only imagine what this scale looked like. Now we can see it directly, said Liad scientist Cole Tambury. The breakthrough also shows how ground-based and space-based missions now work in tandem. As Inouye dissects the sun's surface and low atmosphere, NASA's Parker Solar Probe flies through the solar wind itself, while ESA and NASA's Solar Orbiter studies eruptions in flight. Together, they are beginning to stitch a complete picture of how stars shape the space around them. Knowledge that matters not just for curiosity, but for protecting the technological skeleton of modern life. Inouye's success is part of a larger effort led by NSF's NOAA lab, which coordinates telescopes across Chile, Arizona, and Hawaii. Their projects range from studying dark matter and dark energy to preparing the sky mapping power of the upcoming Vera C. Rubin Observatory. At the same time, these projects acknowledge the cultural weight of their sites, from native Hawaiian lands to Chilean deserts, grounding cutting-edge science in conversations about heritage and meaning. In the end, the Inouye telescope is more than an instrument. It is a lens on both wonder and survival. The sun gives us light and warmth, but it also hides the power to disrupt our lives in an instant. By piercing its magnetic heart with unmatched clarity, we're finally learning to read its moods, turning what was once mystery into a warning system. and reminding ourselves that even the star that sustains us must still be watched. In September 1859, the sun reminded Earth just how small and fragile we are. That was the Carrington event, the most powerful solar storm ever recorded. Two British astronomers, Richard Carrington and Richard Hodgson, spotted an unusually bright flare on the sun's surface, unaware that a massive wave of plasma was already racing toward Earth. Hours later, the sky erupted. Auroras shimmered as far south as the Caribbean, telegraph lines sparked and caught fire, and operators discovered they could send messages without batteries, powered only by the strange currents induced in the wires. It was chaos, but in a world lit mostly by candles and gas lamps, the damage was limited. Jump ahead to October 2003 when the so-called Halloween storms hit. This time, the world was wired and vulnerable. Satellites blinked out, spacecraft faltered, astronauts on the ISS huddled in shielded areas, and Sweden lost power for an hour. In South Africa, a dozen high-voltage transformers were fried beyond repair. Flights over the poles were rerouted to avoid radiation spikes, and auroras painted the skies as far south as Texas and the Mediterranean. Shockwaves from the event rippled outward, detected not only on Earth but by probes orbiting other planets, even reaching Voyager, 2 in the depths of interstellar space. For the first time, humanity caught a glimpse of what a true solar superstorm means in the digital age. The sobering reality is this. If a storm on the scale of the Carrington event struck today, the fallout would be global and catastrophic. Our power grids, sprawling and interconnected, are magnets for disruption. Quebec's 1989 blackout showed how quickly things can collapse. Millions left without electricity in under 2 minutes. A stronger storm could knock out transformers across continents, equipment that takes months to replace, plunging entire regions into prolonged blackouts.
A similar storm today could have a catastrophic effect on modern power grids and telecommunication networks. According to a study by the National Academy of Sciences, the total economic...
And it wouldn't stop there. The internet, the invisible bloodstream of the global economy, is more fragile than most realize. Undersea cables that link continents are lined with signal-boosting repeaters, and each one is vulnerable to geomagnetically induced currents. A single storm could fry them silently, cutting continents off from one another for months. Cloud servers, banking systems, digital trade, all could grind to a halt. Planes flying over the poles would face dangerous levels of radiation and lose radio contact. GPS signals, already delicate, would scatter and falter, taking down the timing systems that keep financial markets synced, power grids stable, and logistics running. Farmers guiding tractors, cargo ships navigating oceans, even emergency responders rushing to crises. Suddenly they'd be blind. The true danger is not in one system breaking, but in all of them collapsing at once. Power going down means no internet. No internet means no financial trading, no logistics, no modern communication. Satellites fried or thrown into safe mode would cripple navigation and weather forecasting. Within days, societies could spiral into panic. And our exposure is only growing. Renewable energy plants tied into massive grids create new points of weakness. Thousands of satellites in mega constellations like Starlink are sitting targets for space weather. The rise of autonomous vehicles, drone networks, and space-based services embeds this fragility deeper into daily life. We are building a civilization more dependent on the sun's mood than ever before. The Carrington event once lit up the night sky with awe. The Halloween storms gave us a warning. The next time the sun sends a storm of that scale our way, it won't just spark a few wires. It could bring the whole world to its knees. Preparing for it is no longer optional. It's survival. Even before Inouye opened its eyes, humanity had already built a scattered watchtower network for the sun. NASA and NOAA operate satellites like the Solar Dynamics Observatory, which stares at the sun in dozens of wavelengths, capturing eruptions as they bloom. The Solar and Heliospheric Observatory, a joint ESA-NASA mission launched in 1995, still keeps vigil, blocking the sun's glare to track coronal mass ejections racing into space. More recently, the twin stereo spacecraft gave us stereo vision, letting scientists follow eruptions in 3D for the first time. Together, they've created a constant stream of solar weather reports, images and measurements that feed into NOAA's Space Weather Prediction Center. Pilots, power companies, even astronauts rely on those alerts. But the warning time is painfully short. Most of the time, we know a storm is coming only after it has already left the sun, leaving less than a day, sometimes only hours, before impact. For a true superstorm, that's the difference between saving a grid and losing it. The gaps are clear. Satellites can watch, but they can't see the magnetic fields braided beneath the surface, where eruptions are born. They can measure particles streaming by, but not predict which tangled sunspot will actually blow. That's why Inouye matters. It brings the fine detail that satellites can't, zooming in on the fingerprints of magnetism before it erupts. And that's why Parker and Solar Orbiter matter. They don't just see the storm, they taste it, flying straight into the solar wind to measure the particles and fields firsthand. We are, in a sense, building the sun's medical chart. Each new mission adds a vital sign, temperature, pulse, blood pressure, so that one day, instead of reacting to solar outbursts, we can forecast them like hurricanes. Today's network is remarkable, but it is also fragile, dependent on aging spacecraft and a patchwork of instruments. A single failure leaves blind spots. The dream is to turn this patchwork into a system, ground telescopes, orbiters and probes all linked together, warning us not just that a storm has happened, but that it is about to. For the first time, humanity has built a three-pronged eye on the sun. In Hawaii, the Daniel K. Inouye Solar Telescope peers across 10,000 feet of sky to deliver the sharpest Earth-based images ever taken of the solar surface, resolving details as small as 20 kilometers wide. From orbit, ESA's Solar Orbiter tilts its view to catch eruptions from the side and even glimpse the poles, regions long hidden but critical to decoding the sun's magnetic cycle. And then there is NASA's Parker Solar Probe, diving closer than any spacecraft in history, plunging straight into the corona to taste the plasma and magnetic fields where solar storms are born.
So the orbiter's first close approach to the sun has enabled us to, for the first time, operate all 10 instruments on board together.
Each of these missions is groundbreaking on its own, but together they form a synergy unlike anything before. Parker samples the storm directly, Solar Orbiter watches its unfolding in space, and Inouye captures the tangled knots of magnetism at the very surface where it all begins. Linking their data allows scientists to follow a solar storm from its first spark to its impact on Earth, the way weather satellites, ocean buoys, and radar together decode Earth's climate. For centuries, flares and coronal mass ejections seemed sudden, unpredictable flashes of violence from the sky. Even now, the best forecasters can usually give only hours of warning. But this coordinated toolkit, ground-based precision, space-based surveillance, and in-situ sampling promises something new: prediction. Over the coming decade, scientists hope to track how energy slowly builds in twisted strands of magnetism, why some regions remain quiet while others erupt, and how those eruptions accelerate particles that stream outward through the solar system. The vision is simple but profound: forecasts of solar activity as precise as our daily weather reports. Warnings that tell us not just if a storm is coming, but when, how strong, and which regions of Earth will feel its impact. The stakes couldn't be higher. Power grids, GPS, satellites, aviation, finance. Modern life depends on systems fragile to geomagnetic disruption. A storm like the Carrington event of 1859, if it struck today, could cripple continents. But with real forecasting, operators could reroute loads, satellites could be placed in safe mode, astronauts on the ISS or on the moon could shelter at the right moment. What was once an unpredictable hazard could become a manageable risk, an invisible but vital layer of planetary defense. And beyond the practicality lies something deeper. For most of human history, the sun was unknowable, a blazing disk worshipped, feared, or endured. In the 20th century, science began to peel back its layers, but the view was still blurred. Now, with Inouye's razor-sharp images and Parker's daring dives into the corona, we are finally beginning to see the sun for what it truly is, a dynamic, living star. The effort is not just science for science's sake. It is about learning to coexist with the star that sustains us, to anticipate its moods, and to protect the fragile civilization we've built in its light. We are, at last, beginning to read the sun's heartbeat.
The probability that will happen. Some we get a little bit more lead time and we can put out warnings for, and some we just can't. We can only alert when they begin to happen.
The sun is no longer just a symbol of warmth and light. It's a force we must learn to forecast as carefully as hurricanes. With Inouye, Parker, and Solar Orbiter working together, we're closer than ever. Each flare mapped, each storm tracked, brings us one step nearer to protecting Earth's fragile heartbeat.